Hi, Science 10. So I gave you that extra day. Most of you have gotten the test done, so that's great. Um, those of you who haven't, please try to get that in as soon as possible. Okay, so that is going to be for Mark. So it's an open book, it's a take home exam, so you should be able to get that done. So the next topic will be kind of a small unit just on radiation. Um, so at the end of it, I'll give you a little quiz, a take-home quiz. So I'll spend about three classes on radiation, and then we'll get into the motion unit, which is a longer unit. So I've got these two sheets here. Like if you're unable to print these off, then you can just use a separate sheet of paper to write your answers in. These are also the worksheets that I want you to complete for next class. So first off, let's start off with um, an isotope, what an isotope is, and the notation. So an isotope is basically the same element that has a different mass number. So first off, the notation that you're going to look at, uh, here's the notation. So X represents an element, and then you're going to have two numbers, one on the top left and one on the bottom left. The top left is going to be the mass number, and the bottom left is going to be the atomic number. So the atomic number is the same thing as the number of protons, and the mass number is the number of protons plus the number of neutrons. Okay, so let's say here's a periodic table. Okay, so and they'll might be slightly a bit different, but let's say we're looking. Oh, let's just look at the one at the top here. Okay, so there's silicon, and there's the atomic number. Okay, so that 14 there tells you that your atomic number is 14, which means that you have 14 protons. Okay, if we're looking at nitrogen, you have 7 protons. Okay, atomic number 7. So the periodic table basically, as you go left to right, beginning with hydrogen, and then helium, and then lithium, you're just going left to right, you're going up by 1. Now, you notice on the bottom here it says atomic mass. This is not the same thing as mass number. Atomic mass is basically a weighted average that's looking at all the naturally occurring isotopes in nature. So, for example, if we look at oxygen, it's got a weighted average of 16. So what that tells you is most of the isotopes of oxygen would be mass number 16. You'd have some 15, some 17, but overall the average would work out to 16. Okay. Now, what we'll look at today is what we call decay reactions. So when something is unstable, that's another way to look at it as being radioactive. Radioactive means it's unstable, and what that means is the element, the way it's configured, can't basically hold itself together, and it's going to start to fragment. So parts of it are going to break off, and in doing so, you get one of these three typically are accompanying what is being released. So alpha, beta, and gamma. And when we talk about radiation safety, one of the things we look at is how penetrating is the radiation. So alpha is very weak, so your skin can block it. Beta is more penetrating, so you would need something like aluminum to block it. And then gamma is very penetrating. You would need something like lead to block it. So gamma is the one that we're most concerned about when we talk about any type of nuclear fallout. Like, for example, if a nuclear power plant exploded, we would be worried about the gamma radiation in addition to the explosion itself, because it's so penetrating, it'll get into the cells, and then that can lead to things like mutations, and it's also a carcinogen, right? So that can lead to cancer. Remember, we talked about that when we looked at the DNA sequencing. Now, the symbols for gamma, so is this this letter there, and 00 indicates it has no mass number or no atomic number. Beta, there's the beta symbol B, or it can be E. So basically, a beta particle is an electron, and the atomic number here is -1. This is just a little bit of a typo, just to can cross that out there. Okay, and then alpha is given as 4 over 2. So mass number 4 and then atomic number 2. So an alpha particle is essentially a helium isotope. Okay. Now when we talk about isotopes, the way we distinguish one isotope from another is by saying the element and then the number after it. So for example, if I said uranium 235, what that basically means is I'm talking about the uranium element, and then 235 represents a mass number. So U235 is different than U238. Okay, those are two different mass numbers. So remember, the atomic number, the number of protons, that's fixed. So it doesn't matter what isotope you're talking about, like carbon 12 or carbon 14, they'll both have the same number of protons. The only thing that will differ for an isotope is the mass number. And mass number, again, is the number of protons plus neutrons. So if your protons are fixed, the only thing that's going to alter the mass number then is the number of neutrons. So it's a difference in neutrons between one isotope and another that causes the mass number to be different. So you can find out what the characteristics of gamma, alpha, and beta are by completing the remainder of this sheet. Let's go to the second sheet. So here are some of the reactions. Now we spent a fair amount of time on the chemical reactions. Remember the single replacement, double replacement, etc. All that type of stuff, where we talked about combining things and then making sure that we balance them in terms of the number of atoms on both sides of the arrow. So these are radioactive or nuclear equations. It's done a little bit differently. I actually think you'll find this easier than what we just finished looking at with the chemical equation. So basically what you have to do here is you have to have the numbers on the top have to be the same on both sides. So notice here you've got a mass number of 32. That means this side should also be 32. And then here you have a mass number of 15. That means this side should also be 15. Okay, so what you have to look at is, how do I get them to work out? So if this is 32 and that's 32, that means the number on the top here has to be a 0. Okay? And then if this is 15 and this is 16, then the number here has to be a -1. Right? Because 32 plus 0 is 32, 16 minus 1 is 15. So that's what it says here. The sum of the mass numbers does not change. The sum of the charges does not change. So the numbers have to add up. Now, what has a 0 minus 1? That's going to be your beta particle. So this is a beta decay. Okay, let's look at the next one here. Now, right off the bat, for the next one, because this is an alpha particle, I know this is an alpha decay. Okay, because it's producing an alpha particle, just like this is a beta decay because it's producing a beta particle. So now what I do is I say, okay, this is 4 on the top, that's 218, so this has to be 214. Okay, and then that's 84, this is 2, so this has to be 82. Okay, so again, the numbers on the top have to be add up to the same on both sides, and the numbers on the bottom have to add up to be the same on both sides. Now, I need to know what element this is, so what I'm going to use is the atomic number 82. So I use the periodic table, and then I look at 82, and 82 is going to be right there. Okay, so that's lead, which has a symbol of Pb. Okay, so that means I can put the symbol here of Pb. Okay, lead, so that one's done. Okay, so a beta particle is this one here, right? Or you can also use 0, -1 with that beta symbol. An alpha particle is this helium 4-2, or you can use 4-2 with the alpha symbol, which is this one. Okay. Now, what happens with the gamma? So the gamma is a little bit different. So remember, gamma is this one here. Okay, so 0, 0. with this symbol. Okay, so this is a gamma decay. So notice that nothing is, because you just got zeros, nothing is changing. So see how this is 2412. This is also going to be 2412, and 12 is magnesium. So how do you know a gamma decay is going to start? Is because of this little star on the top. This star basically means that you have an excess of energy. Okay, so you have an excess of energy, too much energy, that the atom can't contain it. And so it needs a way to release that energy, and it does so via a gamma ray. This is actually not a particle, it's a ray. So this is like pure energy that's being released. Okay, so that's what we mean by a gamma ray. Okay, so what you want to look for is that star. So if I gave you a question and I just said, let's look at this one here, number 7. If I said PO216 is undergoing a beta decay, you should be able to complete the remainder of the reaction, because I already told you it's a beta decay. So in this case, it's given to you. But if you know a beta decay is being produced, then right away you can figure out that this is going to be there, and then using the numbers you can figure out what's missing. Okay, so let's do this one. So 0 here, 216 there, so this is going to remain 216. That's 84. This is -1, so this one has to be 85. Right, and now what we have to do is figure out, okay, what's number 85? So let's use the periodic table, and 85 is going to be the element AT. Okay, so if you don't have you should have had a periodic table for when we're doing the chemistry unit. Same table would work for what we're doing here. Okay, so what I want you to basically get out of today's class, and again, you're going to have to use some technology here to look up things, but I want you to know what the difference between an alpha, beta, and a gamma ray are. Alpha particle, beta particle, and a gamma ray, and how the decay reactions are different. Understand what the numbers represent in isotope notation, and then I'd like you to be able to do these nuclear equations. And again, I don't think you'll find these as difficult as the chemistry equations that we were doing. Okay, so finish off these 2 sheets, and then I'll go over the answers to these for Thursday's class. Okay, and then we'll continue looking at some things having to do with radiation. Okay, so again, if you haven't handed your test in yet, make sure you do so, and then let's get this done for Thursday's class. Okay, so again, stay safe, and I'll talk to you soon. Bye now.